Okay, so these are some other strategies for integration, things that may be helpful when you are trying to do an integral. So one of the strategies is to complete the square. It is very helpful for changing integrals into things that we think are too hard to integrate. So our first one is going to be technique 1. And this is to complete the square. Okay, so the first one I have is the integral of 2 over, okay, you gotta move. This little thing gotta move because you're in my way. Okay. X squared minus 6x plus 10 dx. Okay, so as we look at it, if we try to make u equal to x squared minus 6x plus 10, then du would be 2x minus 6 dx, and that's not going to work for us. Okay, we don't have du in the problem. So let's complete the square on the denominator. So we have x squared minus 6x. We have plus 10 is x squared minus 6x. I'm going to put the plus 10 over here. And so now if I take half of 6, I get 3. And I square it, that gives me 9. So I'm going to add 9. But I need this to still be the same, so I need to subtract 9 off. Okay, so now the x squared minus 6x plus 9 plus 10 minus 9 looks the same. Does everybody see that I have not changed the problem? I added on 9 and I subtracted it right back off. Okay, so now by doing that, this piece becomes x minus 3 squared. And then I have just plus 1 left over. So therefore, I can take my integral and I can rewrite it as the integral of 2, not what I wanted to do, undo, of 2 over, and now I'm going to write it as x minus 3 squared plus 1 dx. And so now it actually looks like something I can work with, okay? Because now it is the sum of 2 squares. So now if I let u equal x minus 3, and I let a equal 1, and then I let du equal to dx, then this thing just becomes the integral of 2 dx is du over u squared plus 1. So now if I pull the 2 out, I get du over u squared plus 1, and you should recognize that as what? What is that integral? Okay, now I made it into something I recognize. Go back. What was our learning objectives? To integrate integrals using techniques to convert them into other known integrals. Aha, something I recognize. What is the integral of that?
Would it be 2 ln u squared plus 1?
Okay, almost, Gustavo, but is there a u in the numerator? In order to do ln, I gotta have the derivative in the numerator.
Would it be like the inverse tangent?
Okay, so that's the tricky thing. The ln and the inverse tangent look very much alike because they have something in the denominator and they don't have, the question is, if I have a u, I can use the ln. Okay, so that was a good attempt. But if I don't have a u, I have to use the tan inverse. Gustavo, you with me?
Yes.
Okay, all right, good. All right, so we're going to do 2 times the tan inverse of u over 1. So this becomes 2 times the tan inverse. U is x minus 3 plus a constant. Okay. All right, so that's one type. Here's another one. Where is, I thought I had another one. Oh, here's one. Okay. So here's number 2, the integral of d theta over the square root of 2 theta minus theta. Okay, so theta squared. Okay, so here's another one where I want to complete the square. So I'm going to write 2 theta minus theta squared as negative theta squared minus 2 theta. Okay. So now I'm going to write this as negative. I have theta squared minus 2 theta. If I take half of the 2, I get 1. If I square it, I add on 1. But here's the thing. Look at the fact that this negative is distributed, right? So since the negative is distributed, I actually have negative theta squared plus 2 theta, which is what I had on the left-hand side, but I've now subtracted 1, so I have to add it back on. So this now gives me 1 minus, and that thing becomes theta minus 1 squared. Okay, so this integral becomes the integral of d theta over top of the square root of 1 minus theta minus 1 squared. And that, again, now let's make the substitution. U is theta minus 1, A is 1, du is d theta. So this now becomes the integral of d theta over the square root of 1 minus u squared. And that should be du. I apologize. Okay, does anybody recognize that?
Would it be sine inverse?
That's sine inverse. Good. So this is the sine inverse of u over a. A is 1, so plus a constant. So this is sine inverse of u, which was, where is u? Theta minus 1 plus a constant. So completing the square can be very helpful. Okay, so that's one thing. The next technique that we can use is separating a fraction. Okay, so you may have the integral of 3x minus 2 divided by x squared plus 6. Okay, so now if I let u equal x squared plus 6, then du is equal to 2x dx. And I don't know what to do with that -2. So therefore, this won't work. It's better if I separate it. So I'm going to separate this thing into 2 parts. So the first integral is the integral of 3x over x squared plus 6. And then the second part is the integral of, well, -2. Of 1 over x squared plus 6. Now, somebody tell me something about either integral. I don't care which one you want to start with. This one I'm going to call I1, and I'll call the other one I2. So what do you know if somebody choose something to say about either one?
I think in the first one, we can do U substitution.
Okay, so I1 is U substitution. Okay, so we can let U equal to x squared, and du is 2x dx, and then x dx is 1/2 du. Okay, so I1 becomes 3 times the integral, the x dx is 1/2 du. And I'm sorry, this is x squared plus 6. I wrote it wrong. And then the denominator is x, is just u. So this is 3/2 the integral of du over u. What is that? What is
ln.
natural log, absolute value of u plus a constant. So I1 is 3/2 the natural log of the absolute value of x squared plus 6. Okay, what's I2? Gustavo, what's I2? Because now you see where we used the log in the first one because we had an x. So the second one doesn't have an x. So what are we going to have to do with that?
We still need to integrate it. Can we integrate it by we can't do that one by partial fractions, right?
No, that would be because it's a plus. You're right. We can't do partial fractions. This is one that just looks like something we've already done.
So would
This-
it be 2 ln x squared plus 6?
Okay, that's what we got for the first piece because we were able to use the x. So in the first piece, we were able to do the ln because we had an x here. So we were able to make this u, and then we could do du, and that's how we got ln for the first one. But the second one, I'll give you a hint. It looks like dx over x squared plus a squared.
Is that the cosine inverse?
No, the cosine inverse is negative dx over the square root of a squared minus x squared. That's the cosine inverse one. This is the same one we danced around last time.
So tangent inverse.
It's another tan inverse. So here, a is equal to a squared is equal to 6. So a is equal to the square root of 6. Gustavo, you are thinking. Thank you. So I2 is the integral. I think there was a number in front of it. Well, it doesn't matter. We'll put that in front. So therefore, we're going to get 1 over the square root of 6, the tan inverse of x over the square root of 6. And so now my original integral, which was, oh, that forgot a dx. How did I do that? 3x minus 2 over x squared plus 6. Is the first one, I1, which was 3/2. The natural log of the absolute value of x squared plus 6. And then we get minus 2 over the square root of 6. The tan inverse of x over the square root of 6. Now I can add my constant and I'm done. Okay. Any questions?
Dr. Lott,
Yes.
I think this homework is already due. It was due yesterday.
Yeah, that's because we're a day behind. So I will go in and fix that date.
Okay.
Okay, yeah, we're a day behind. Thank you for reminding me. Okay, I'm just going to do one more technique. There are lots more that we can do. We can keep going forever. This one is dividing if the power is higher, if the power of the numerator is higher than the power of the denominator, we need to divide the fraction first. Okay, so let's try. So technique number 3. And that is reducing an improper fraction. Okay, so let's say we have the integral of two x cubed plus 1 divided by x squared minus 5x plus 6. Now, we learned how to do partial fractions, and in all the partial fractions, the numerator was either equal to, the numerator was smaller than the denominator. For all the partial fractions one we did. But if the numerator is equal or greater, then we have to reduce the thing first. Okay, so in order to reduce it, I'm going to use long division. So I want to do x squared minus 5x plus 6 goes into 2x cubed plus 0x squared plus 0x plus 1. Notice how I make sure I have placeholders for the ones that are missing. Okay, so x squared goes into 2x squared, 2x cubed, 2x times. And then we multiply. So I get 2x cubed. I'm going to get minus 10x squared. I'm going to get plus 12x. and then I'm going to subtract. So now I'm going to get 10x squared minus 12x plus 1. Okay. X squared goes into 10x squared 10 times. So now I'm going to get 10x squared. And then I'm going to get minus 50x. It's a pretty big number. Plus 60. And then I'm going to subtract. So now I'm going to get 38x minus 59. Is that right? 38x minus 59. So on. 10x squared minus 50x. 38. And then plus 60. Yep. Okay. So now I can't go any further. So now I know that 2x cubed plus 1 divided by x squared minus 5x plus 6 is equal to 2x plus 10 plus the remainder. So the remainder is 38x minus 59 divided by x squared minus 5x plus 6. So now I've reduced it. These two are whole pieces, but OMG, I have to use partial fractions on this. So now I have to do 38x minus 59 over x squared minus 5x plus 6. And I can see that that factors into a over x minus 2 plus b over x minus 3. And then once you find those parts, find a and b. Okay. Then your problem looks like the integral of 2x cubed plus 1 divided by x squared minus 5x plus 6 dx simply becomes the integral of 2x plus 10 plus a over x minus 2 plus b over x minus 3 dx. And so my answer becomes x squared plus 10x plus a, whatever that is, times the natural log of x minus 2 plus b times the natural log of x minus 3 plus a constant. So the only part that I didn't do was the partial fractions here. Okay, so use partial fractions here. So just use your roots, guys. Find your major equation. And use your roots. Oh, by the way, the exam. The partial fractions question was an extra credit question because that was not included in the sections. So that was an extra credit question. Some people got some points. If I did not see the major equation, I don't know how you factored that thing and got that answer that quickly or whatever. So you didn't get all the credit. Okay, so but then this one you just, now that we've reduced it from an improper fraction, because improper meaning the degree of the numerator is higher than the degree of denominator, we factor it to down to here where we do the partial fractions, find a and b, stick them in, and you have an answer. Okay, so those are the major 3 techniques. There are a couple others, like, you know, of course, separating your derivative, separating the denominator, and some other things. But I just wanted to show you those 3 major techniques. Okay, any questions?
Well, Dr. Watt,
Yes.
for when you're dividing the or when you're about to put in the partial fractions and you have when you got 2x plus 10 as the major function, was 10x squared supposed to be negative, or was it supposed to be something else?
No, because it was, oh, good question, good question. Oh, I love it. Okay, so when I did x squared into 2x cubed, x squared went, okay, so I multiplied it back out. So I got, oh, okay, so when I multiplied 2x squared, I got 2x squared minus 2x cubed minus 10x squared plus 12x. I subtract off this whole thing. And so when you subtract 0 minus a negative 10x squared, it becomes positive.
Okay, thank you.
Same thing, I subtract off this whole line, which is why I took negative 12 minus a negative 50 and got positive 38.
Okay, thank you.
No problem. Excellent question. That's how I got 1 minus 60 gave me negative 59, okay? All right. I may send out, I probably will put up just a few more techniques in the document section, just so you guys can see what kind of ways to do some intervals. Oh, that was one. Oh, I need to do that one. I need to do this one. Technique 4. A different U substitution. Well, I'll just call it U substitution. Integral of x plus 2 times the square root of x plus 4. Okay, so as I'm looking at that, that looks kind of crazy. I have x plus 2 on the outside and x plus 4 on the inside, and I'm not sure how to integrate that. So this one, the most difficult thing is on the inside. Let that be u. So let u equal x plus 4. Now solve for u. Solve for x. So x becomes u minus 4. And dx, du is just dx. Okay, so this becomes the integral. X is u minus 4 plus 2. And then this becomes the square root, or u, to the 1/2 power du. So I let x plus 4 be u, and then I can solve for x to be on the outside, figure out what that needs to be. So then that just becomes x is u minus 4. So here's x. Uh-oh, it didn't do what I wanted. Here's x. X is u minus 4. X is u minus 4. Okay, so now this is the integral of u to the 3/2 minus 2 u to the 1/2 power. Because 4 minus 2 gives me -2. And then I take the u, so that's what I get. That's easy. This is 2/5 u to the 5/2 power minus 4. Nope. Yeah, 4/3 u to the 1/2 power plus a constant. That is not right. That is not right. Add 1 is 3/2. 2. That is right. Add 1. Oh, that's what's wrong. This should be 3/2. I wrote it wrong. This is 3/2. And that should have been 4/3. That was right. Okay. So therefore my answer is 2/5. U is x plus 4 to the 5/2 power minus 4/3 x plus 4 to the 3/2 power plus a constant. So that looked like that was going to be a hard integral, but if I just solve for x after I put in what u is, I'm good. Okay, any questions?